Hey students, welcome back. This is week 4 of your digital online learning at home. Fun, fun, fun. This week we're going to be talking about light. Last week was sound. The week before that, waves, and then energy started this whole shebang off. So we're really getting into this now. At this point, you should get the general idea of what we're doing and how we're doing it. But if not, uh, you can always ask me questions through email or just read the directions. Either one will work. We're going to have Google Meets this week as well. I'm just going to start this video off by introducing the week's work, and then we'll get into the concepts about light. So the general idea this week is to describe energy as a property of an object associated with light, this week really light, and describe how light energy is transmitted by waves. So let's just start with the weekly update. If you have not looked at the weekly update yet, come on, what are you doing? This is the easy place to figure out what you're doing for the week. You could listen to me or you could just read it, but I'm going to go through just the very, very broad strokes here. Final grades, they will be due, really, I'm going to be finishing up grading work this weekend. That'll be the last time I'm going to be putting in new grades, is this weekend. I'm very clear about that. Don't ask me next Friday, hey, Mr. Sender, you know I'm your buddy, can I have an A even though I had a D? I'm going to say, guys, you need to go back in time and invent a time machine or something like that. And just do your work. It's simple as that. If you already had a pretty good grade, you're not going to have a grade go down. If you've been doing your work, you've definitely seen your grade go up. It's simple as that, but I'm not trying to be mean at all. I'm just saying the grades will be kind of worked through this weekend and posted early next week. So get your work done this week. Try and get it done by 3:15 on Friday if you possibly can. We will have Google Meets at these times this week. This week, instead of having 5 lessons, since it's a shortened week, we're going to have 4 instead. Happy Memorial Day. Maybe one last thing I'll talk to you about is the elective preference form. If you have not completed that, they've postponed the deadline till this Friday, so you still have a chance to do it. Please go on to click these links down here, the course catalog and this Google form, which will take you into basically tell the school what you want to do next year for your electives. It's not a guarantee that you're going to get those electives, but it's a chance to tell the school what you want at least. And they do take that into account, I know for sure. Hey, on Class Dojo 2, the class schedule, which I linked in my weekly update, but also just important stuff here. Make sure you're paying attention to this from Mr. Minna. Maybe one more thing to mention, parent survey. Please ask your parents and guardians to take the district survey. There's a link down here that helps out with the school's overall ranking, which is one small part, but it's a part nonetheless of how Baldy is the #1 middle school in Philadelphia. So back to this now. What is light? I'm not going to lie, this is the 3rd time I'm trying to do this video, and I hope that this time it doesn't get erased. Dearly hope. But I love light so much that I'm just excited to tell you about it. Please do have your notes out. That'll be your guided notes from, I'm going to try and pull it up for you right now. So your guided notes from lesson 1, which are posted to this assignment, the nature of light. You notice there's only 1 page this time. I'm going to try and keep these to shorter lessons and shorter guided notes this week. I've been getting some feedback from you guys saying you're just a little bit overwhelmed here. Trying to listen to that and respect that. So you respect the fact that you should still be taking notes, and we'll all be happy, right? I'm trying to reduce it. Please don't take that as a mean to say, oh, we don't have to do it now. It's just trying to reduce it, so make sure you do it well. Okay, so the nature of light. You got yourself all ready here. Well, light is a wave. We've talked about that multiple times. In this whole review here, right, waves can really be categorized a couple of different ways. We can say they either need stuff to go through, that would be mechanical waves, and that stuff would be a medium, or it doesn't, which is electromagnetic waves, right? It can be longitudinal, which is a wave that gets created by a back and forth disturbance, and the wave travels in the same direction as the disturbance is going back and forth in, or transverse, which means the disturbance is going up and down, and the wave is traveling perpendicular to that. Kind of like if you were to drop a pebble into water, the pebble will move the water up and down, but the wave will move sideways, so it's perpendicular to the direction of the vibration or the disturbance. So in this whole classification scheme, light is an electromagnetic wave. It doesn't need something to go through because it travels on electromagnetic basically fields, and it's transverse in nature. What is it? Well, let's just try today to explain the relationship between visible light, the electromagnetic spectrum, and sight. So light is a form of energy emitted by the sun, and other things too, but just going back to our lessons on energy, we know that light is a form of energy. We really call it radiant energy, but we're just going to start calling it light from now on, okay? So it's radiant energy, but what the heck is it? It's enough to say it's a form of energy, but what is creating that energy, right? How is it that the sun just ends up pushing out light from its nuclear energy? We know that that transformation happens from nuclear energy to radiant energy, but it's not saying what the actual radiant energy is. And this was puzzling to people for a very long time. You would not be the first person to think about this, right? So like if you're thinking, what the heck is light? Take a second, pause the video, and think, what is it? Okay, and hopefully you're back now after thinking about that for a second. You have now entered into this investigation that people have been doing for hundreds of years, trying to figure out what light is. We'll go back to even Isaac Newton. Isaac Newton thought that it was a particle. He was a pretty smart dude, wrote physics basically, wrote calculus, but even he got it wrong a little bit. For a long time, people believed that he was right. Light is just a particle that passes like a tennis ball getting thrown by something. But then some people did this experiment, this guy named Hooke, not the pirate, even though he was English, and who knows if he had a hook for a hand. His name was just Hooke, H-O-O-K-E. And he did this famous experiment called the double slit experiment that kind of proved that light acts as a wave. You take, basically in this experiment, you take a piece of something, we don't call it paper, we're just thinking about it as paper, right? With two small slits, much smaller than this. And you take yourself a flashlight, also known as electron beam gun. It's not nearly as dangerous as it sounds. It's just basically that shoots out a single particle at a time. So, this has been done with a couple different things, but in this experiment, electrons, he shot the electrons through this piece of paper, we'll call it, with two slits in it. Now I want you to imagine for a second, what would the piece of paper behind this piece of paper look like? What would that look like? If you were shooting light through these two slits here, what would the paper behind it look like? Did you end up saying something like this? Yeah, this is what you would look at, right? And like nobody picks that. Nobody thinks that. It's just a weird thing. But when people say, what the heck? That's usually where science starts. So people had a question like, so why is it that we expect one thing, like maybe two big squares on the back of this paper, and we get 5 different squares, and it actually just keeps going off in each direction? Well, people start to line up what they understood about waves. That they interfere with each other, and they can interfere constructively and destructively, right? And the fact that if you were to have waves passing through this slot here and this slot here, slit here, they would interfere with each other as they diffract around that edge in a pattern similar to this. If you'd imagine, like, you drop a pebble here and a pebble here in a pond, they would get these waves that overlap, and you'd have areas of constructive interference, which are these darker areas, and destructive interference, which are these places where it basically gets canceled out. It's understandable if you don't quite understand that. And all that's to say is that this was a good proof that light is a wave, or at least acts as a wave, because waves interfere with each other, right? Particles don't interfere with each other. You shoot a tennis ball through one of these slots, it's going to hit the back of here somewhere, right? It wouldn't interfere with the tennis ball all the way over here, but waves do this. So this is one of those things where they say, well, if it acts like a wave, then it must be a wave. That basically was accepted for a long time. Another person came along, you might recognize this person, Albert Einstein. Albert Einstein, even though he agreed with this as being a good explanation for this, he still wasn't completely sold that light is just a wave. He really thought it's a particle as well. Just another good video about what this is, the double slit experiment here. This breaks it down a lot better. And then I can show you in just a quick slide there. So if you want to, pause the video and take a look at that. Pause the slides and take a look at that video. Okay, so Albert Einstein, he thought about another experiment people had been doing, but hadn't explained yet why it was working the way it was, called the photoelectric effect experiment. basically people have been shooting photons, or we'll just say they've been shooting light onto a metal surface, right? And nothing happened. It didn't shoot anything back off of it, didn't reflect, it just absorbed. And these little blue dots down there represent electrons caught up on the metal surface, right? It didn't matter how bright that yellow light was, it just wasn't making those things do anything. But then they would turn up the frequency of the light to something more blue or violet, and all of a sudden, boom, 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 these electrons start shooting off the surface, very much in the same direction as the light was, so they call them instead photoelectrons. And you're saying, so what the heck does this mean? Why would you ever explain it like this? This is a good proof of light acting as a particle. It's hard to explain it, but the best way I can break it down is just by saying whatever is causing these electrons to shoot off must have momentum, because what gets something to move without momentum? You think about, like, if I were to run into you in the hallway, I'm kind of a big guy, you might have fallen over, right? Or you might have gotten pushed in that same direction. Accidentally, I'm saying, right? But what wouldn't happen is you wouldn't just move all of a sudden without somebody pushing you in the first place, right? It doesn't happen. Unless there's somebody giving you momentum, something giving you momentum, it wouldn't just get momentum. Well, these electrons have a very real momentum, and it has to come from somewhere. Therefore, the photons, or what Albert Einstein would say, are packets of energy. You can say like a particle. These packets of energy come in like particles and boom, hit these electrons and get them shooting off with momentum. Why only this light instead of this one is a much more complicated explanation we just don't have time for. So Albert Einstein got his Nobel Prize for that. He didn't get it for relativity or E equals mc squared, right? He got it for the photoelectric effect, explaining that light acts as a particle and a wave, what we call a duality. So light is a form of energy that travels as an electromagnetic wave, but we call the particle of light, it's not that there actually is a particle, but just the thing that kind of explains it as a particle, a photon. It's called a packet of energy, a quantum of energy. It basically, this energy rides along in a wave caused by two fields that get generated at the same exact time, called the magnetic field and the electric field. They are very similar. It's basically, not even going to try to explain it, the differences between it, because I don't think I'd be able to get the meaning across in this point. But these fields are potential fields, right? They have an ability to push energy into, I'm sorry, not energy, but force basically these packets of energy called quantums of, or quanta of light called photons. They are able to apply a force to it, and they just keep vibrating back and forth perpendicular to each other. So as they do that, it pushes the energy along the x-axis and out at a very, very quick speed. And basically, the faster these things vibrate back and forth, you have a change in color and frequency, basically, of the light. And depending on how far they go up, more force, you have brighter light, whether that's visible light or invisible light. And I'm going to stop the video here, and we'll talk next about, like, well, when can you see it, and get much, much more simple. But I didn't want to, I think you guys are very smart, and you should be able to pick up some of this. And if not, go look it up online right now. Okay, so take a second to stop the video and then go to the second video, and I'll see you there.